Hello, everyone, and welcome to the Midterm 1 Mastery assignment. You can use this as a way to review for Midterm 1. Think of it as like an exam review sheet. And if you understand all the concepts here, you should do fabulously well on Midterm 1. So hopefully you've tried everything on your own before you watch this video key. But either way, let me know if you have any questions about any of the topics we're going to cover. All right, so let's go ahead and start with question number 1. So it says, describe whether primary, secondary, or tertiary alcohols can be oxidized or not. Give examples of each. Which reagents can be used? And what type of product is formed. Okay, so I'm going to go ahead and draw out a primary alcohol. And you could have drawn a different one, that's fine. And then an example secondary alcohol. Let's do 2-butanol. And then maybe an example tertiary alcohol. All right, so now that we have these drawn out, let's think about their oxidation reactions. So primary alcohols can be oxidized to an aldehyde, and they can also be oxidized to a carboxylic acid. And the conditions to get there are different in each case, right? So if we're going to oxidize to an aldehyde, the alpha carbon, right, will be the carbon that becomes double bonded to the oxygen. So we might draw that like this. And sometimes people draw in the hydrogen here as well, right? So we'll make sure to label that as an aldehyde. And then we can also oxidize all the way up to a carboxylic acid. Secondary alcohols can only be oxidized to ketones. And then, right, tertiary alcohols, they cannot be oxidized. So we'll go ahead and add in the reagents. So we want to use PCC to stop at the aldehyde stage with the primary alcohol. Sometimes you might see like dichloromethane or a solvent mentioned, but that's not required. And then for a carboxylic acid, we would want to use a stronger oxidizing agent such as sodium dichromate. And under acidic conditions, that will form chromic acid, which will oxidize in situ. And secondary alcohols, you could use either, right? So you could use PCC or sodium dichromate. And you would get the ketone. All right, let's move on to question number 2. Provide the name of the it should say following. Okay. Explain the steps on how you got the full name. Okay, so we are looking at functional groups here, right? I see that I have a fairly long carbon chain, some alkyl substituents. I have a chloro substituent. There's an alkene, right? And then there's also an alcohol. So given all of these functional groups, the alcohol has the highest priority. So it will be in the parent. And when you have both an alcohol and an alkene or an alkyne, the alkene or alkyne also gets included in the parent. So we're going to make sure that the alkene and the highest priority alcohol get included in the parent chain. So, and of course, we want to think about stereochemistry as well, right? We want to think about, is this R or S, right? And then if you have an alkene, you want to ask yourself, is that E or Z? So that information will come at the beginning of the name as well. But for now, we'll just work on the rest of the name and then make sure to include stereochemistry at the end. So I'm going to start counting from the right, working my way left, because I want to get to the alcohol, so the carbon bearing the OH group, and get the lowest number possible for that, right? So I need to start on this side and not going the other direction. And we want to go on the longest carbon chain that also includes the alkene, right? So that would be 9 carbons, right? So then our parent, right? So the prefix, right, for 9 carbons is non, right? So NON. And then we want to call it a nonene because of the alkene, right? And then a non-enol because of the alcohol. And we want to go ahead and put in those locants as well for the alkene and the alcohol. So we have non, right? For the alkene, 7. So 7-ene and then 3-all. And then once we have the parent, we want to think about what are the substituents, right? So we have the methyl substituents. There's 3 of them, right? So we have for substituents, right? We have a 2,5,5 trimethyl. And then we also have this chloro group, right? So also an 8-chloro. And then looking at alphabetical order, right? So we'll do the parent first, kind of, it says to explain, so I'm kind of adding in the steps here, right? But for the alphabetical order, we would look at C, right, for chloro, versus M for methyl. So remember, tri is a counting prefix, so it doesn't count towards the alphabetical order. And then we'll put in the next step, right, which would be stereochemistry. So I'll go ahead and come over here and let's look at some stereochemistry. So for the chiral carbon, right, we have priority number 1. The hydrogen that's coming out at us is priority number 4, right? This will be priority 2, and that will be priority 3. So it's going to go 1 to 2 to 3, right? That looks like a counterclockwise rotation. But remember that our 4th priority group is coming out at us, so we actually switch it to a clockwise rotation, right? So the stereochemistry here, right, is R, and that's at carbon number 3. Technically, you don't need the 3. You could leave it off because there's only one chiral center. But it's not wrong to also include it. And then for the alkene, right, we want to come over here and look and see, is this E or Z, right? So in order to determine if it's E or Z, we want to look at priority groups attached to the same sp2 hybridized carbon. So between chlorine and methyl, right, chlorine has a higher priority than carbon. So this group would have priority. And then between hydrogen and carbon, the carbon would have priority. So the 2 priority groups, right, attached to the sp2 hybridized carbons are the chlorine and this carbon, right? So this becomes then a Z alkene, right? So you could do 7Z or just Z. Okay, so we want to put that in the front of the name. So putting this all together, and again, if we want, we can just leave off the 3 and 7 because we could still figure it out since there's only one alkene and one alcohol, or one chiral carbon. So we could do, right? Oh, I wanted to do this in red. We could do RZ, and then we come over here to our substituents, 8-chloro, 2,5-trimethyl, and then non-7-ene-3-all. We'll put a little box around our final answer. All right, let's move on to the next question then. Describe the order from most acidic or lowest pKa to the least acidic or the highest pKa. So that's where some useful information, like if you did know some pKa values, that would be helpful, but you could also figure it out using ARIO, right? So some pKa knowledge that might be helpful is that carboxylic acids generally have a pKa of about 4 to 5, right? And alcohols generally have a pKa anywhere from like the 16 to 18 range, right? So maybe you say approximately 17. So those could be helpful. We might not know the pKas of these, right? And that's okay, because again, we can also use ARIO analysis, right? So what does ARIO stand for? Stands for atom, right? Resonance, induction, and orbital. And we apply this in order, right? So if we look at the atom, well, we want to look at the atom attached to the hydrogen that's going to be removed, which is, right, bolded. So it is oxygen, right, in all cases. So that is not going to help us figure out which one is going to be more acidic. So we're going to have to move on to resonance because there was no difference in the atom, right? So for resonance, we want to ask ourselves, once that proton is removed, how many of these compounds are resonance stabilized, right? So we can think about the carboxylic acid, right? So once that proton is removed, we have the carboxylate ion, and we can draw the allylic lone pair pattern, right, to show us that that is resonance stabilized. But that's not the only one with resonance. We can also look at this structure, which would also be resonance stabilized for the conjugate base. So that's the conjugate base, and we can still apply the allylic lone pair resonance pattern. Okay. So we'll come back to that. Let's just go ahead and keep going right through the rest of ARIO. So induction, right? Induction is the presence of nearby electronegative atoms that can help stabilize a negative charge, right? So this structure has a chlorine atom, right, which is helping to pull some of this electron density away, right? Sort of, so we'll just make a little note here. The nearby chlorine, right, helps stabilize the negative charge on oxygen via induction. Due to its electronegativity. Okay, and then it looks like we don't really need to consider the orbital because we see that we have two that have resonance, one that has induction, and then one that doesn't have resonance or induction, right? So we don't really need to consider because we've basically figured out the difference in all of these cases. Okay, so when we're looking at the most acidic, right, do we think it's more stable to have a negative charge on two oxygens, right? So this is the hybrid is the true structure. So both of these oxygens share the negative charge. Or, right, an oxygen and a carbon. So definitely the negative charge will be more stable on two electronegative oxygen atoms. So this should definitely be predicted to be the most acidic or have the lowest pKa, right? So if I called this A, B, C, and D, and I came down here and wrote most acidic, right, to least acidic, and I realize you can't see what I'm writing, that's okay, or lowest pKa to highest pKa. Right, we want to start putting these in order. So then D, right, had the best resonance stabilization, followed by B. It would come down here and write D, then B, then C had inductive stabilization, and A did not have either. Okay, so that would be our order. Next question, provide the reagents to accomplish each transformation. Explain why those reagents produce the major products shown. Okay, so, oh, you know what? I think that there was an error here in the number of carbons because somehow we went from 5 carbons to only 3 carbons. So I think I accidentally left those 2 methyls off there. So sorry about that. Hopefully you weren't too confused. Maybe I'll go ahead and try to fix that on the mastery assignment. Okay, so from here to here, right, what we want to add across the double bond is a hydrogen here, and at the less substituted carbon, we're going to add an OH, right? So we're adding a hydrogen and an OH across the double bond, and we want it to go, so sort of maybe write some notes, right? Add a hydrogen and OH across the double bond. And then it's going to go, because it's 2 different groups, we want to ask ourselves about regioselectivity. And it's going to go anti-Markovnikov. Because the OH ends up at the less substituted carbon. So the conditions to do that are the hydroboration oxidation. So we want to remember how to those reagents, right? So we want to do BH3 THF followed by sodium hydroxide and hydrogen peroxide, and those can be written in either order. And then going in this direction, we see we're also adding H and OH across the double bond. And now we have Markovnikov regioselectivity because the OH ended up on the more substituted carbon. I'm going to go ahead and talk about this one before I write in the reagents, because there's actually two sets of reagents that do Markovnikov hydration of an alkene. And we call that hydration because we're essentially adding water or H2O across the double bond. So we can do oxymercuration, demercuration, or we can just treat it with dilute aqueous acid. So maybe if we analyze this one, right, we'll think about where we should put those two conditions. So this one is strange because it looks like this OH group has migrated, right? So this one could be due to rearrangement, right? Because the OH is not attached to one of the two sp2 hybridized carbons from the original alkene. Instead, it's actually shifted one carbon over. So if we had gone through a carbocation intermediate, right, where the carbocation was secondary after proton transfer and putting a proton here, then we could have undergone a hydride shift to get a tertiary carbocation, right, and end up with this rearranged product. Okay, so we could think of this as also sort of adding H and OH, right? Added. And it went Markovnikov. However, it underwent rearrangement. And so we would want something that goes through a carbocation in order for that rearrangement to take place. So we would just use our dilute acid here. So you might see this as H3O plus or H2SO4 or H3SO4 water, anything like that. It all means the same thing. And then in order to do hydration with Markovnikov regioselectivity and no rearrangement, then we do the oxymercuration, demercuration conditions. So we want to remember how to write that, right? So mercuric acetate, water, followed by sodium borohydride in the second step, right? So both of these give a Markovnikov hydration product, but these conditions are subject to rearrangement, and these conditions are not. Next question. Provide the reagents to accomplish each reduction reaction. List the functional group in the reactant and the product. For the alcohol, list whether it is primary, secondary, or tertiary. Okay, so there's lots to do here, right? We can maybe start by labeling the alcohol, right? That could be a good place to start here. So primary alcohol, and that's the same in the second case here. And then in the third reaction, we have a secondary alcohol. Okay. And then it's talking about reduction, right? And this one says it's going to be via one reduction or via two reductions, right? So if we're only doing one reduction, then we're probably starting from an aldehyde here, right? So we just want a 3-carbon aldehyde. And then to reduce an aldehyde to a primary alcohol, we can either use sodium borohydride, and then sometimes this will mention a alcohol with it, like water or methanol. And then we could also use the stronger reducing agent, lithium aluminum hydride. So oftentimes that's just abbreviated LAH, or sometimes it's written out LiAlH4. But either way, it's lithium aluminum hydride. And then typically it says 1,2 because we cannot mix in the water until the reaction has taken place. So we need to sequentially add the reducing agent followed by water, because these two would react together if they were mixed in together. Okay, via 2 reductions would be starting from either a carboxylic acid or an ester. And I think this is asking for the carboxylic acid because there's no mention of another alcohol here. So we'll just go ahead and do that example. And then if we are going to do 2 reductions, then we typically need excess of the reducing agent, right? So oftentimes it might say excess LAH and followed by water. So this could be the carboxylic acid, or it also could be, and I'll just kind of put this off to the side, an ester. All right. Moving on to the formation of the secondary alcohol, we would reduce ketones to a secondary alcohol. We want to draw the ketone in the box here. That can be reduced and then draw in the reagents. Again, you can either use sodium borohydride. And again, this methanol might be water or another alcohol. This is the important part of the reagents, or lithium aluminum hydride. And you might see water or H3O plus in the workup for that. Okay. So we have, let's wait for this to attempt to, you can do it. There it goes. Okay. Describe how to calculate the oxidation state of a primary alcohol, an aldehyde, and a carboxylic acid. Show how each is related via an oxidation reduction reaction. Okay, so let's just give an example then of again, a primary alcohol, right? And then draw an aldehyde. And we'll draw a carboxylic acid. So when it talks about calculating the oxidation state, they actually want you to calculate the oxidation state of the carbon, right, that is being either oxidized or reduced depending on which way you're going synthetically, right? So they want us to calculate the oxidation state, right, for this carbon, the alpha carbon here, or the carbonyl or carboxyl carbon. Okay, so how do we do that, right? Remember that it's a calculation that's kind of similar to formal charge, except for we count the electrons differently or assign the electrons differently than we would for formal charge. But it kind of helps me at least to remember how I would calculate formal charge and then think about what I would do differently, right, to calculate the oxidation number. Okay, so first of all, you can think of this as like a carbon, right? And it's attached to another carbon. That would be this one. It's attached to an oxygen, right? And then it's attached to two hydrogens. So sometimes it's helpful also to think of it this way, right? Whereas this carbon is a carbon attached to a carbon, a hydrogen, and then double bonded to an oxygen. This carbon is double bonded to an oxygen, single bonded to another oxygen, and attached to another carbon. So for formal charge, I would take the number of valence electrons, which for carbon is 4, and then I would subtract the number of assigned electrons, and that would be 1 for each bond. So in all cases, it would have a formal charge of 0 because there's 4 minus 4 bonds, right, which is 0. But for calculation of oxidation state, we assign the electrons differently. Specifically, what we'll do is anything that's more electronegative than carbon will get all of the electrons. Anything that's less electronegative than carbon will give up its electrons to carbon. And if it's the same atom, we would just split them 50-50, right? So we can kind of think of this as carbon, and it's got the 2 electrons from each bond to hydrogen because hydrogen's not as electronegative as carbon. It will take 1 from the carbon-carbon bond, 50-50 split, and then the oxygen is actually assigned both electrons in this bond because oxygen is more electronegative than carbon. So you can sort of think of it as oxygen has those 2, carbon has these 4, and we're going to do a 50-50 split here, right? So if we do a calculation, we would do the number of valence electrons minus, right, the number of what we call assigned electrons. So it's the exact same calculation as formal charge, it's just that we're assigning the electrons differently because now we're assigning the electrons to the more electronegative atom. And before we were just giving 1 to each atom no matter what the atom was bonded to. So we would have a case of 4 minus 5, right, is -1. So for this carbon, right, oxygen would get all 4 of those electrons. Carbon would get the 2 from the carbon-hydrogen bond, and we would split those, right? So we would have 1, 2, 3. So we would have 4 minus 3 is +1. Let's look at this last one really quickly. So we have carbon. Oxygen is getting all of those electrons, and we have a 50-50 split for the carbon-carbon bond. So this would be 4 minus 1 is equal to +3, right? So if we think about our oil rig, or Leo the lion says grr, right? We know that oxidation is loss, right, of electrons, or the other way to think of it is, so Leo, right, lose electrons, oxidation. So losing electrons, electrons are negatively charged, right? If we're losing electrons, we're losing negative charge or getting more positively charged. So it makes sense that this is, right, represents an oxidation. So we would have oxidation, and then another oxidation, right? And then the reverse process is also true, and that we can convert back, right, through a series of reduction reactions. Okay, so if we look back to question number 1, we have actually already summarized the oxidation conditions, right, for a primary alcohol. So we know that using PCC will give us the aldehyde, using sodium dichromate will give us the carboxylic acid, right? So you can copy this if you want over here, or we'll just go ahead and focus on the reduction in this case. And then I'll just make a little note here that oxidation reactions of primary alcohols was reviewed in question number 1, right? So then we're going to want to think about, okay, what about the reduction conditions? And now that I think about it, did we review those as well in a different question? I think we did. I have a very short memory, don't I? We did review, right, the reduction of a carboxylic acid and then the reduction of an aldehyde back to a primary alcohol. So that was question number 5. So we'll say reduction reactions to make primary alcohols was reviewed in question number 5. Okay, so coming back up here, let's see if we answered all of the questions here. Describe how to calculate the oxidation state of a primary alcohol, an aldehyde, and a carboxylic acid. I guess maybe it would have been helpful to label these, right? So we have our primary alcohol, aldehyde, and a carboxylic acid. Show how each is related via an oxidation reduction reaction. Okay, I think we did all of that. Looking at the next question, describe the multi-step reaction sequence necessary to convert an aldehyde to a ketone. Provide an example reaction sequence. Okay, so we want to think about, right, how would we convert an aldehyde, right, through multiple steps into some sort of ketone, right? Maybe we'll make that ketone. So this is just an example reaction, right? Other examples might vary, right? Maybe we only added a methyl, or we added something other than ethyl. As long as it's a ketone, right, it would be a reasonable example reaction here. Okay, so we have not learned any reactions to do this in one step, right? There's no way to do that in one step. However, we can do it in 2 steps, right? So one of the things we might want to think about is the fact that we've started with 3 carbons, right? And we ended up with 5 carbons. So, and it's always good to sort of count your carbons, right, in the starting material and the product. So we know that we are going to be adding 2 carbons, right? So we're forming then a new carbon-carbon bond. And remember that one reaction we've talked a lot about in the chapters that are on the exam, right, it is the Grignard reaction. So we should be thinking about, right, doing a Grignard reaction. Okay. So we are actually set up to do a Grignard in the first step because we know that Grignard reagents attack aldehydes and they form new carbon-carbon bonds. So that is definitely looking like it will be something we might want to do here, right? So if we start with this aldehyde, right, and we think about doing a Grignard reaction, we definitely want to add these two carbons, right, because they're not present in the starting material. If we treat an aldehyde with a Grignard reagent with two carbons, then we will end up with a secondary alcohol where we've made that new carbon-carbon bond. And then once we have the secondary alcohol, we can oxidize that secondary alcohol up to a ketone. So we've sort of outlined our path, and now we want to come back and add in some reagents. So we can do a 2-carbon Grignard reagent, right? So we want to do ethyl magnesium bromide, followed by some sort of acidic workup. That will provide us with the secondary alcohol, right? And then we can do an oxidation. And again, from a secondary alcohol to a ketone, we can oxidize with PCC or with sodium dichromate, right? So we could do PCC and then just in parentheses, we'll write, or we also could have done sodium dichromate under acidic conditions. That would also do the oxidation that we want, right? So we've started from an aldehyde. We did a Grignard reaction to form a secondary alcohol, right? And then we did an oxidation to form a ketone. All right, let's look at the next question. Provide the missing reagents to accomplish each synthetic step. Describe the position of the alcohol with respect to the new carbon-carbon bond being formed and how that can tell you which type of electrophile is used, aldehyde or, well, I guess it should have given more options here because it could be a ketone, right? Or an epoxide. Well, maybe we have something else we should add here, okay, to the question. Okay, so let's go ahead and take a look, right? So we're starting from this alkyl halide for 4 different reactions involving forming a new carbon-carbon bond. And we also then have the conversion of an alkane to an alkyl halide, right? So we know that we can convert an alkane to an alkyl halide through radical halogenation. So we would want to use Br2 and heat or light, right, to do this radical halogenation reaction. Right, and always look and see what direction that arrow is pointing. Okay, once we have the alkyl halide, this can be turned into a Grignard reagent with the treatment of magnesium metal, typically done in an ether solvent. So we are going to be adding in various electrophiles to form each of these products, right? So because this is a secondary alcohol, right, we should add an aldehyde in this case. Right, over here we have a tertiary alcohol, right? So we're going to use a ketone in this case, right? And when it talks about the positioning, right, with respect to the new carbon-carbon bond, you can think about where is the new carbon-carbon bond, right? So this carbon is now getting attached to each of these carbons, right? So this one here is the new carbon-carbon bond. Let me draw it right here. Right, and then if we do some counting, we can say this is carbon 1, 2, right? 1, this maybe would be 2, 2, since they're both attached to 1. And then if we come over here and think about this, this was the new carbon-carbon bond, right? And the same thing right here. Okay, let's do the same sort of counting. So 1, 2, right? 1, 2, 3. So what this is asking us to notice, right, is that the alcohol is on carbon number 1, right? So we'll make that note. Alcohol is on carbon number 1, right, which is the same as this one. Which is different than these bottom 2, where the alcohol is now at carbon number 2. But carefully looking at the relative positioning of where the alcohol ends up with respect to the new carbon-carbon bond, we can know which type of electrophile to use, right? In the alcohol chapter, we learned about adding aldehydes and ketones. Those alcohols always end up on carbon number 1, or the carbon directly attached to the carbon in the alpha carbon in the alkyl halide. If we, in the next chapter, we learned about the use of epoxides as an electrophile with Grignard reagents. When we use an epoxide, we end up with the alcohol at carbon number 2 with respect to the new carbon-carbon bond, right? So now we're going to know why we should use, right, an epoxide in these two cases down below. And if we think about the fact that we're adding 2 carbons here, that means that our aldehyde that we're using should also have 2 carbons, right? Because we're making this new carbon-carbon bond and we need to add both of those 2 new carbons. So we can, in all cases, we're going to start by adding magnesium metal, because we need to form the Grignard reagent, since we're the starting material is shown as the alkyl halide. Now, the second step is when we're going to add in the different electrophiles that we're going to use, right? So we said we're going to use a 2-carbon aldehyde here. So we're going to use ethanal. And then over here, we're going to use a ketone. We're adding in a total of 3 carbons, right? So we want to use a 3-carbon ketone, or in this case, just acetone. For the epoxides, right, we look and see how many carbons did we add. We added 2 here and 3 here. So we're going to use a 2-carbon epoxide followed by, in this case, a 3-carbon epoxide, right? So 2-carbon epoxide would just be ethylene oxide. And then 3-carbon epoxide would have an additional methyl, right, on one of them. I could have just drawn a line, right, and I decided to add in the CH3 just for clarity. Okay. Now, usually some acidic workup is also mentioned in each case, right? So I'll go ahead and add in the H3O plus third step in all of these reactions. And that provides the proton for the alcohol, right? And also quenches any excess Grignard reagent. All right, so looking at question number 9, describe reagents that can convert a primary alcohol to an alkyl chloride. Okay, so this is just looking for, one example in each case. So we could do, or if you can think of more, that's also okay as well. So primary alcohol to an alkyl chloride, let's come up with an example here. So primary alcohol, right? Draw in an alkyl, so a primary alkyl chloride that would make. And then if we think about what conditions we can use here, right? We could use HCl. Remember that we do need a way to make a good leaving group, right? The OH group is not a good leaving group for substitution reactions. So typically we need something to create a good leaving group. In this case, we're using an acid, right? So these protons will be used to convert the OH group to H2 plus, and then water is a much better leaving group. So chloride will do an SN2 reaction to kick out water, right? You may have also seen in the book some alternative conditions, right? Such as, so we'll put in some alternatives, right? SOCl2 is one the book likes to use a lot. And I think they even give you another option of zinc chloride. Okay, what about reagents that can convert a primary alcohol to an alkyl bromide? So very similar, right? In this case, we're just drawing the alkyl bromide. So we would want to switch from HCl to HBr. And that's mainly it, unless you could find some zinc bromide or something. Okay, describe reagents that can convert a secondary alcohol to an alkyl chloride. All right, so let's do a secondary alcohol. And again, we're going to convert, same idea. And if you wanted to, you could even use a chiral example, right? So this could be up, and you might be converting this to the down chloride through an inversion process. So that is one way. In fact, why don't we go ahead and do that, right? So we'll just say, okay, what if this was, right, chiral, decided to use a chiral example. So we should look at inversion. So if we were using a chiral substrate, you would probably want to use a two-step process to make sure that the entire thing goes through SN2 so that we get 100% inversion. Remember that if we promote SN1, we could get some racemization, right, or form a racemic mixture, which is less valuable synthetically. So we need to get a good leaving group, and we want to avoid SN1. So we don't want to use an acid. The other way to get a good leaving group is through tosylation, right? Forming the tosylate, that converts the OH to OTS, which is a good leaving group. Then we can just use some chloride, which could be supplied through sodium chloride or potassium chloride, and that will do an SN2. So similar idea, secondary alcohol to an alkyl bromide. right? What would need to change about these reagents? We are just going to change the second step so that we get bromide. So sodium or lithium or potassium, bromide, etc. What about a tertiary alcohol? Right, so let's say just a simple one, right? Either getting converted to a tertiary alkyl chloride or a tertiary alkyl bromide. And what conditions would we do here? So in this case, both of these are going to go through SN1, right? Because this is a tertiary carbon. Tertiary carbons don't undergo SN2 reactions, so they'll undergo SN1. So it's fine to just use acid, right, to convert these. So we would want to use HCl or HBr. And in this case, we cannot use like SOCl2 because that requires a SN2 reaction, which would require a less hindered or less substituted alcohol. All right, this is a long activity, so I'm going to go ahead and take a break, and then I'll come back in a little bit. All right, I'm back, so let's get started again. Question 10, what reaction do these conditions promote on an alcohol reagent? Give at least 2 example reactions using different substrates. So these conditions, concentrated acid and heat, promote an E1 reaction, right? And an E1 reaction would work best on a tertiary alcohol. So I'll just give a couple of tertiary alcohol examples, right? So we could do something like this, right? And then maybe something with a ring. And then the products would be the alkene, and we want to make sure to draw the Zaitsev product since E1 always favors the Zaitsev product. So we would, right, draw that, and then over here, the Zaitsev product would put the alkene in the ring. Okay, so we are looking at oxidations. So I feel like this is pretty similar to a question we did already, but that's okay. We'll go ahead and go through that anyway. So we have primary alcohol, and it's via one oxidation. So we'll oxidize it to an aldehyde. And then we can also oxidize it through 2 oxidations to a carboxylic acid. And then the different conditions would be PCC to get the aldehyde and sodium dichromate to get the carboxylic acid, which I forgot to draw. All right, moving down a little bit lower, we're also looking at oxidizing secondary alcohols. Remember that tertiary alcohols don't oxidize, and secondary alcohols oxidize to ketones. And then the conditions for that, we can use PCC, which again stands for pyridinium chlorochromate, or sodium dichromate. Question number 12, provide the missing reagents to accomplish each synthetic step. Okay, so we can really start anywhere we want to here. Let's look at going from a terminal alkyne and converting to either a ketone or an aldehyde. So these would be hydration reactions, either Markovnikov or anti-Markovnikov, and then a tautomerization of the resulting enol, either to the methyl ketone or to the aldehyde form. So if we want to get the Markovnikov hydrate, we want to use conditions similar, right, to what you would see with an alkene. With an alkene, if we were doing the Markovnikov hydration, right, we would do oxymercuration, demercuration. And again, we would want to make sure to use conditions that avoid rearrangement on a substrate like this, right, because this is giving us the non-rearranged product. Right, and then rearrangement would happen if we used H3O plus, and then don't forget that hydroboration oxidation works for anti-Markovnikov from an alkene, so BH3THF, hydrogen peroxide, and sodium hydroxide in the second step. Okay, so again, this is really in a way similar, right, to the alkene. So we want to use mercuric sulfate and H2SO4 in water, right? So if you sort of remember one, right, you can helps you to remember the other. And then if you wanted to get the anti-Markovnikov hydrate, which tautomerizes to an aldehyde, we want similar conditions to the anti-Markovnikov reaction from the alkene. The only difference is when we start with an alkyne, we use a bulky borane instead of BH3, which we would use with alkenes. So we would use 9 bbn instead of borane with the same second step. All right, the next question, provide the missing reagents to accomplish each synthetic step. So notice how this one's sort of going in opposite directions here, right? So we'll want to pay attention to that. So from here, we're starting with the secondary alcohol, doing a elimination to either get the Hoffman product or the Zaitsev product, right? So we can kind of take some notes here, right? This represents the Zaitsev product. This represents the Hoffman product. And so we would want to use a bulky base to get the Hoffman product and a non-bulky base to get the Zaitsev product. But because we're starting with a bad leaving group, right, we also want to think about starting off with a tosylation. And we would want to do that in both cases because we need a good leaving group regardless of which alkene we're trying to target. The difference, right, lies in the second step here. So I'll kind of highlight that with a different color. We have potassium terbutoxide here, right, versus a smaller base. So you could use sodium hydroxide, sodium methoxide, or sodium ethoxide. So I'll just use the smallest one as an example. Okay, so once we have the alkene, then we just need to add H and Br across the double bond, right? So that's what's happening whether you go up or down. So we're either adding H and Br Markovnikov or H and Br anti-Markovnikov. So we want to then Note that Markovnikov would just be HBr. Markovnikov or anti-Markovnikov would add in HBr with peroxides. So in this case, Markovnikov is actually going the opposite direction, going down, because the bromine is ending up on the most substituted position here. So we would want to write HBr. And then anti-Markovnikov is the reaction going up here. So HBr and peroxides. All right, so it says provide the name, again, of the following. Explain the steps to how you got the full name. Okay, so it looks like we have a ether, right? But remember that there really isn't a way to name ethers. These are this is just a methoxy substituent, right? And we're going to name it as an alkane. So we want the longest carbon chain. There's 5 carbons in this ring, but there's 1, 2, 3, 4, 5, 6 carbons outside of the ring. So we're going to go with an alkyl chain outside of the ring. If we were to start on this side, we would not get to the first substituent till carbon number 4. But starting from the top, we get to the first substituent at carbon number 2. So that's the correct way to number the parent chain, right? So step number 1, we identify the parent, right? Which in this case is just hexane. Okay, so step number 2, we identify and name the substituents. Sometimes I like to circle those so that I don't forget any. Right, so we have a variety of substituents here. We have a 2-methyl, a 2-cyclopentyl, and a 3-methoxy. Again, none of those have any sort of priority. So we're just looking for alphabetical order in terms of knowing which order to put them in front of the parent. So M, we would use methyl. C, we would, for cyclopentyl, we would use C because cyclo is not a counting prefix, so it counts towards the alphabetical order. And then again, M for methoxy, noting that when we find a point of difference here, the O comes before the Y alphabetically. So in terms of the number or the order in which we put these, right, we would do cyclopentyl first, then methoxy, then methyl. Lastly, we would look if there's any chiral centers that are indicated with a dash or a wedge, or alkenes, and there are not, right? So we don't need to do anything additional to name this, right? We can just move on to the name at that point, right? So you might say 3, stereochemistry, and then I'm just going to put none here. Okay, so putting that all together, we have 2-cyclopentyl, 3-methoxy, 2-methyl, and then the parent hexane. All right, looking at the next question. Explain why, hopefully this will focus. Explain why similar sized alcohols have the highest boiling point compared with ethers and alkanes. What intermolecular forces is each exhibiting, right? So for example, we could do ethanol versus dimethyl ether versus just propane. Okay, so sorry, I was just thinking about something. Anywho, going back to intermolecular forces, we have hydrogen bonding. Right, we have dipole-dipole. And London dispersion forces, right? And then these two would be only dipole-dipole for the ether, right? And London dispersion forces. And then only London dispersion forces for the alkane. Maybe I'll write that in. Right, so maybe I'll just put an X, no hydrogen bonding. Right, and then no hydrogen bonding or dipole-dipole in the case of the alkane, right? So we would expect the, for example, boiling point to increase as we experience stronger and stronger intermolecular forces. Describe when a Williamson ether synthesis would not be successful. What is important to know about the alkyl halide specifically? Give some examples. Okay, so we want to, again, looking at that, right? When would it not be successful? Okay, so the alkyl halide must be primary, ideally. So methyl primary, or in some cases, secondary would be okay, but not tertiary because we're relying on an SN2 reaction. So for example, if we had an alcohol and we were trying to do a Williamson ether synthesis, right? If this was a tertiary alkyl halide, right, then this would not be successful. And then we'll just make a mention here that the alkyl halide should be unhindered to promote a successful reaction. Right, and then maybe some more information, right? Tertiary alkyl halides do not undergo SN2 reactions. Right, so, and we need this to undergo an SN2 reaction in order for this to work. Okay, so we'll write second step is an SN2 substitution reaction. So after the first step, we would have the alkoxide, right after sodium hydride deprotonates the alcohol. And then if it attempted to do an SN2 reaction, right, on a tertiary alkyl halide, we would do, right, big X, right? That does not work. Okay, so let's maybe give it a successful example. Or two, right? We can definitely add in this ethyl group, right? Because it would come from a unhindered primary alkyl halide. Let's maybe give one more example. You could also use a phenol. Oftentimes with phenols, we use a sodium hydroxide as base just because phenols are more acidic. So they don't require the stronger sodium hydride base, right? We can use sodium hydroxide in the case of a phenol. And here's an example where we're using methyl bromide or methyl iodide, right? And this is very unhindered, so it would be a successful reaction. So we'll say primary or methyl alkyl halides are the most successful due to being able to do a fast SN2 reaction. All right, next question. Describe the difference between oxymercuration, demercuration, and alkoxymercuration, demercuration. Which produces alcohols and which produces ethers? Give several examples of each. How can you work backwards from the structure of an ether to get the two organic reactants, the alkene and the alcohol, that could be used to make the ether? Okay, so let's give some examples here, some sort of background information, right? So it says it wants us to compare the oxymercuration, demercuration, right, versus the alkoxymercuration, demercuration. Sort of a compare and contrast here. Okay, so typically they show the alkene as the starting material in these reactions, right? So for example, let's give a couple of examples, right? Maybe we would look at a substrate like this or a cyclic structure, something like that, right? And we'll just do the same substrates over here for the alkoxymercuration. And then we're going to look at the differences in the reagents and similarities in the reagents, and then the differences in the products. So if we are doing oxymercuration, demercuration, we will be using mercuric acetate and water, right? And the alkoxymercuration, demercuration uses mercuric acetate and an alcohol, right? So I'm going to make those a different color just so it kind of stands out, right? So the difference here is we would be using water versus an alcohol. And then the second step is the same in either case, sodium borohydride. And let's draw in the product. haven't left myself too much space here, but I'll try to squeeze it in. So we want to put the alcohol right on the more substituted carbon, because this is forming the Markovnikov hydrate product. And over here would be very similar, except we're forming an ether, right? So methanol, so I'll put OCH3 on, right? So maybe I'll make a note that this is formed an alcohol and this formed an ether. All right, so we had another example as well. So again, we'll just copy out the reagents from up above. We always use water for the alkoxymercuration, or oxymercuration, sorry. But we can use a variety of alcohols, not just methanol, for the alkoxymercuration. So I'll use maybe a different one, right, in this case here. So let's draw in the product. So again, we're going to put that OH group on the most substituted carbon, and the OR group also on the most substituted carbon. Did it draw that very well? Oh, well. And we're going to come over here, and I'm just going to put the O with the 3 carbons attached. 1, 2, 3. Okay. So those are a couple of examples and the difference in the reagents and the functional group of the product. And then the second part asks us, how can we work backwards from the structure of the ether to get the 2 organic reactants? And there could be more than one, set of possible organic reactants depending on the substrate. But let's draw an ether example. So let's do something like this. Okay, so how could we work backwards from this structure? What we want to do is think about how we can form an alkene, right, from this. And if there's a more substituted carbon and a less substituted carbon on the alkene, then that would be ideal, because of course the ether will form on the more substituted carbon, right? So we'd want to look for this substituted position here, right? You can kind of add in the hydrogen, then think about having removed that, right? So this is sort of working backwards, kind of a retrosynthesis to giving us an alkene, right? And an alcohol. And this is the more ideal choice than doing it on the right-hand side, just because we would have gotten ethylene, and there would have been no difference in substitution. So usually people would just use a different reaction in that case. But that would also, potentially be a correct answer as well, as long as you are thinking about sort of in reverse, kind of eliminating the alcohol to form an alkene, then you'll have the right answer. Okay. Next, describe how excess HBr or HI and heat can cause the cleavage of ethers. When are both carbon-oxygen bonds in an ether cleaved? What type of carbon-oxygen bond cannot be cleaved? Okay, so let's look at some examples, right? So let's say we have diethyl ether, right? And let's compare that to something like this, right? We could do another example. There could even be a case where it's secondary. That would be totally fine. Let's say we'll do just trying to make it different in each case, right? So we don't have to do too many examples. Let's go ahead and add in a aromatic ring, right? And well, we've already done methyl, primary, secondary, and tertiary, so it doesn't really matter. I will go ahead and just leave it as well, we'll just go ahead and make it a different primary alcohol. Okay, so let's say we are treating this with HBr or HI, and think of those as interchangeable, right? So I'll just, randomly do HBr in the top two, right? And HI in the second two, right? So we'll just put, think of HBr and HI as interchangeable. Okay. And then what we want to do here is look at the carbons, the alpha carbons, right? And then put in their hybridization. So I'm just going to point to the alpha carbons in all of the different ethers here. Okay, so it doesn't matter which way I'm pointing, just as long as I'm pointing at the right carbon, right? So those are those carbons that are attached to the oxygen. So then I just want to come in and write whether or not the carbon is sp2 or sp3. Usually we don't go into cases where the carbon is sp, but if it was sp, it would also not undergo a reaction, right? It has to be sp3 for a reaction to occur. So sp3 in both cases here, right? Both of these are also sp3. So it doesn't matter if it's methyl, primary, secondary, or tertiary, right? We're just looking at whether or not the hybridization is sp2 or sp3. So far, all of those have been sp3, but this one is sp2, and so is this one, right? And maybe I'll even sort of circle those to emphasize them, like that. Okay, so we can only cleave, right, the carbon-oxygen bonds where the carbons attached are sp3. So I'm just going and drawing a line in all the carbon-oxygen bonds that will undergo cleavage. And then I am not going to draw a line to any carbon that's sp2. Oh, I messed this one up down here. Okay, so that one, sorry, is sp3. So we can go ahead and draw the red line for the carbon-oxygen cleavage there. Okay, so then that, whether or not we draw two cleavages or only one, that tells us how many alkyl halides will form and if we're going to get a water molecule. We're only going to get a water molecule if both carbon-oxygen bonds are formed, right? Like in this first case, they're both formed. They're both cleaved, excuse me. So we will get a water molecule that's formed. And notice how it's ethyl on both sides. So that really just gives 2 moles, right? Or double the amount of ethanol, or sorry, not ethanol, but ethyl bromide, because again, the alkyl groups are equivalent or the same. So we're going to form, right, some ethyl bromide and water, right? And you could even mention like 2 times the amount here if you want to do that. In this case, we have an unsymmetrical ether, so we're going to get 2 different alkyl halides. Again, I used HBr, so I'm going to go ahead and make alkyl bromides. And I'm just going to make a tertiary and a methyl, and also water because I cleaved both carbon-oxygen bonds in that ether. But here, right, I'm only cleaving one because this carbon is sp2, right? And sp2 hybridized carbons don't undergo substitution reactions. So they do not undergo SN1 or SN2 reactions, which is why we cannot cleave this carbon-oxygen bond. So we are only going to cleave the bond on the left here to form, in this case, an alkyl iodide, because I randomly chose to use HI in this case. And then this side will remain not uncleaved. So we'll get the, instead of water, we're just going to get this alcohol, right? So we'll get, just draw that alcohol. And then here again, right, we cannot cleave this carbon-oxygen bond because this carbon is sp2. So we'll just draw phenol as one of the products. So no water molecules produced here, right? And also some propyl iodide. Okay, and then I'll just make a note up here that we can assume excess acid in all cases. And acid meaning HBr or HI. All right, looking at the next one, we have give an example of different alkenes, one cis and one trans. Show how epoxidation with MCPBA is stereospecific. Draw the product using two different ways. Okay, so let's go ahead and draw in a cis, right, and a trans alkene. Okay, and then you could even label them if you wanted. Right, so when we're talking about epoxidation, right, we can use MCPBA. Or we can use the two-step process with cheaper reagents, which would be first forming a halohydrin with bromine and water, followed by treatment with sodium hydroxide to form the epoxide. So again, those conditions, just think of those as interchangeable. And we just want to remember that epoxidation is stereospecific. So if we start with a cis alkene, the groups, right, should be syn. So since they're methyls, I just need to put them both up or both down, right? And this is technically a meso compound, right? So I don't need to write plus enantiomer. And with the trans, we want to do something similar here, except for to make sure that we preserve the initial stereochemistry. Oh, I don't know why I just did that up. Sorry. Should be down. Might have to draw this one again in the key and make it look prettier. So these should be syn, right? And these should be anti. And then this one is not a meso compound, right? So technically this one would also produce its enantiomer. Okay, and then it says to draw the product another way. We could do that. For example, we could keep the carbon chain in the plane and then just draw the bonds to the oxygen as dashes or wedges. So for example, if you had like 4 carbons, right, you could And again, I guess I really should have drawn it. Really going to have to redraw this one because I didn't do a good job the first time. Okay, so again, kind of keep it looking like cis or trans, right? Because of the starting material. And then we'll go ahead and put in the 2 wedges on the carbon oxygen bonds. Same thing here. And I could have put these both down instead of both up. So that was just drawing, making a choice. Again, this is still meso, so no enantiomer. This one would have an enantiomer, right? And just by virtue of drawing this methyl down or over in this direction, the stereochemistry at that carbon is different, right? So it is still showing the stereospecificity of the reaction. All right, number 20, label the carbons in the epoxide ring as primary, secondary, or tertiary in the following example. Is NaSH, right, or sodium thiol, considered acidic conditions or non-acidic conditions? What carbon will be attacked by the nucleophile and why? How do we show inversion at that carbon? Okay, so, right, it says first it wants us to do some labeling. So this would be a tertiary carbon. This carbon is attached to 3 other carbons, right? And this would be a secondary carbon. And the conditions, right, are non-acidic because there's no acid here, right? This is Na plus and SH minus, so there's no acidic protons. So with non-acidic conditions, the nucleophile, which is the thiol, or I should really call it a thiolate, will be attacking the less substituted carbon preferentially, right? So we want to show it attacking here, and then the loss of the leaving group arrow as well. And then to show the inversion, this is always tricky for students, but we want to actually not change the dashes and wedges, because showing the nucleophile attached opposite the leaving group has already shown the inversion process at that carbon. So we just kind of want to, right? So I draw the O. So I guess I'm just going to draw immediately what forms after, so I don't confuse anybody, and then we'll draw the product after the workup. So again, we just, because this is a dash, we want to keep it a dash. This is a wedge, we want to keep it a wedge. So we're going to go down, and then 1, 2, 3. And then over on this side, we want to make sure that the nucleophile is shown in the plane, right, opposite that of where the leaving group left. And then this is on a wedge, so we keep it on a wedge. And that's counterintuitive. I know people think, okay, that's not showing inversion, but it is showing inversion, right? Because again, the nucleophile is opposite where the leaving group left. So we have, in fact, inverted that stereocenter. So this is the initial product. It's not isolated, right? This is sort of an reaction intermediate, right? I put brackets around it just to show that this would not be isolated because it's not neutral and stable, right? So we would still need to do a acidic workup, right? So water or H3O plus workup. Water works just because it's in huge excess, but H3O plus is more acidic, so it would be also work to protonate that alcohol. So we would get the same product, right? We just want to draw OH instead of O minus. Okay. So should I make any more notes here? Let's see. Right, so this is a strong nucleophile. And it will attack the least substituted carbon under non-acidic conditions. Right, and then maybe some other notes over here, right? So inversion is shown because the nucleophile, which is SH minus, right, is drawn opposite the leaving group. Right, which is this oxygen. Okay, and then maybe one more note, right? Over here. Do not switch dashes and wedges. Hopefully that's super clear. All right, looking at the next question. Label the carbons in the epoxide ring as either, same as before, primary, secondary, tertiary. Is HCl considered acidic or non-acidic conditions? What carbons will be attacked by the nucleophile, or which carbon, excuse me, and how do we show inversion? Okay, so we have, again, still the same as before, right? Tertiary and secondary, but this is considered acidic conditions because, right, H plus, those are acidic protons. So we can say this is really H plus, right, which is, quote, an acid, and Cl minus, which is, right, the nucleophile. Okay, great. Next, so what carbon is going to get attacked? So we are going to attack the tertiary carbon under acidic conditions. And so the mechanism, right, is going to be more than one step, but we're going to, just like before, but we're going to protonate first because we're treating with acid, right? So we'll go ahead and show the mechanism, and we're going to protonate first because we're treating with acid. So I'm just going to redraw this structure, right, so that I can draw the full mechanism here. So I just redrew that, and I'm going to redraw some HCl, and I'm not going to show it dissociated. I mean, it could be dissociated as hydronium ion, but this is fine to just show it not dissociated. So we can do, right, proton transfer. So again, proton transfer is occurring first because we're treating the epoxide with acid. So that is going to form the same structure, but now the oxygen has an extra proton, one less lone pair, and a positive charge. I'm just copying out the rest of it, the same as it looked before. And now I'm going to show the chloride that got formed in this first step, That's again the nucleophile, right? Doing a nucleophilic attack. We're also going to have simultaneous loss of a leaving group. So this is an SN2-like reaction. So here's the nucleophilic attack arrow, right? Followed closely by the loss of a leaving group arrow. And this represents an SN2-like process here. We're going to take some notes, right? So the nucleophile will attack a tertiary carbon if present. Okay, so if it was secondary versus primary, it would still go to the primary carbon, right? So it only goes to the more substituted carbon if there is a stabilized carbon, such as a tertiary carbon. Okay, so since we have one, it's going to attack there. Let's go ahead and draw the product of that step, right? Maybe I'll write in an SN2-like process. Okay, again, right? We actually do not want to switch any dashes and wedges, right? We just want to show the incoming nucleophile opposite the leaving group. So since it attacked the carbon on the left, I'm going to draw the chlorine over here on the left. And then this is directly going to form OH because the oxygen has already been protonated. I'm just going to keep this the same. So wedge goes to wedge, right? And over here, same thing, just kind of push it up a little bit on the page. But this propyl group will remain on a wedge, and the methyl group will remain on a dash. And we have already drawn the final product here. Put a little box around it. Okay, and maybe take some more notes. So we have, right, we'll make do not switch dashes and wedges. Inversion, just like before, is shown by placing the nucleophile opposite the leaving group. Okay. How could you accomplish the first multi-step synthesis using an epoxide reacting with a Grignard reagent? How could you accomplish the second multi-step synthesis using an epoxide reacting with a hydride reducing agent, such as LAH? Okay, so we want to use a Grignard in the first case, and we want to use a LAH as a reagent in the second synthesis. Okay, so remember what I always say about synthesis: count your carbons. So over here we have 6, 7, 8, right? So we have 8 carbons. And then over here we have 6, 7, 8, 9, right? 9 carbons. So that is a clue, if we didn't already have one, that we need to form a new carbon-carbon bond. And one way to do that is through a Grignard reagent. So right now I cannot do a Grignard reaction because Grignards do not react with alkenes. So I'm going to need to think about whether or not I want to convert this to an alkyl halide or possibly to a carbonyl containing reagent like an aldehyde or a ketone. So if we think about the fact that we're going to be adding 1 carbon, right, and we want the OH group to be here so that it can be oxidized to a ketone. So, you know, essentially what I'm doing is I'm thinking about what would be some key intermediate products here, right? That, could potentially be useful. So my thought is that if the alcohol was here, I would be able to oxidize that nicely to a ketone. So then I'm thinking, okay, how can I, convert this to either an aldehyde or a alkyl halide, such that my alcohol will end up at this carbon. So what I think I want to do is convert it to an aldehyde, because if my aldehyde is here, I'll be able to do a methyl Grignard to add 1 carbon. My alcohol will end up at the right place, and I'll be able to do a oxidation, right? So what I'm thinking is I would like to get an aldehyde here. There's no way to do that directly. So I'm going to have to do multiple steps. And then I'm going to do a Grignard reagent and an oxidation, right, to get to this product. So if we sort of think about that, right, okay, I'm going to draw in my key intermediates here. And a lot of synthesis is just, trying different things and seeing what might work, right? So I know if I have this aldehyde, I can do a 2-step sequence to get to a ketone. The 2-step sequence will involve a Grignard, which will form a secondary alcohol, followed by an oxidation of the secondary alcohol to form a ketone, right? So we would do a methyl Grignard, right? Followed by an acidic workup. And then we would do an oxidation of this secondary alcohol using PCC, right? Or again, we could also use sodium dichromate here. So I'm doing pretty well, right? I've thought about how I could get to a ketone from an aldehyde, which does have 1 less carbon, right? So I was able to add 1 more carbon. So it's a little bit closer to the reactant just by virtue of having only 8 carbons, right? Compared to the 9 carbons in the product. But now I still need to think about what would be a way that I could get from this alkene, right, to an aldehyde. And there's actually more than one potential way you could do this. So you could do a anti-Markovnikov hydration to get to an alcohol and then oxidize it to an aldehyde. Or you could convert this alkene to an alkyne and then do a anti-Markovnikov hydration of the alkyne, which will tautomerize to an aldehyde, right? So there's a couple of different pathways here. And so we'll kind of show, both of them, because they're sort of both 2 steps and equally, potentially equally viable. Okay, so in one case, I'm thinking maybe I'll go to an alkyne. Actually, for the alkyne, I want to go straight, so I'm just going to put the alcohol over here. And in the other case, I'm going to draw the alkyne. Right, and then from the alkyne, I can convert that to the aldehyde directly, and from the alcohol, I can convert that to the aldehyde directly. Okay, so those conditions, right, would be, this is an anti-Markovnikov hydration. So we want to think about using hydroboration oxidation. There is absolutely, you have to know these reactions, right? Even the review reactions are so important for synthesis. And then from a primary alcohol, we can oxidize that to an aldehyde using PCC. If we had thought about converting the alkene to an alkyne, we can do that, but it's actually a 3-step sequence. So first step is just treatment with bromine to form the dibromide. Then we would do double E2 elimination with excess sodium amide, followed by water at the end. So that would get us to the alkyne, and then from the alkyne, we can do anti-Markovnikov hydration to form an enol that will tautomerize to this aldehyde. So from an alkyne, again, if I want to do anti-Markovnikov hydration, I need to use a bulky borane, so I need to use 9 BBN instead of borane with the same second step in either case. Okay, so let's move on to the second case. And remember, it said we were going to use LAH here, so that was our clue. Okay, if we are thinking about this, again, we have 8 carbons. Remember, I always say count your carbons, right? Even if you still have 8 carbons, that gives you some information. Like, I don't need to form a new carbon-carbon bond here because I have the same number of carbons in the reactant and the product. So that's still useful information. But in this case, right, it says we have to use LAH, which is like, that's kind of strange, right? Because I can think of a way to do this without using LAH. So why don't we think about using LAH, because it says we have to in the reactant, and then talk about if we didn't have that constraint, what would be another way to do this multi-step synthesis. So again, there's no way to convert this alkene directly to a ketone. However, I can form an epoxide and have LAH attack the epoxide to form a secondary alcohol, which can be oxidized. So that is one method, right? LAH reacts with epoxide, so that was a good clue to think about making this epoxide. And you always want to think about how is it related to, alcohols or ethers, epoxides, because that's really what we're trying to test on here. And then again, LAH will react with this epoxide to form a secondary alcohol, which we can then oxidize to the ketone. So putting in the reagents here, again, MCPBA, or you could do, right, the 2-step sequence with bromine and water forming the halohydrin, followed by sodium hydroxide. We are going to use LAH. Remember, lithium aluminum hydride will have a hydride attack that less substituted carbon, breaking that carbon-oxygen bond. That's how we get our third hydrogen attached to that carbon. And then water or an acidic workup shown as the second step, followed by an oxidation of a secondary alcohol to a ketone. So we could either use PCC or we could use sodium dichromate. Now I kind of talked about like, okay, what would be another way we could convert this to that and maybe not even use LAH? So one alternate, right, multi-step synthetic pathway that doesn't use LAH, right? So what would that look like? So we could start from the alkene. And hopefully, if you haven't thought about this, you can pause the video, think about what you would do, right? And then see if we come up with the same thing. So from the alkene, I can think about adding an OH group here because that is just a Markovnikov hydration reaction. But I would want to be very cautious here that I use conditions which do not allow for rearrangement, because this is a secondary position right next to a tertiary position. So it's primed for carbocation rearrangement. And then from the secondary alcohol, we can oxidize the same way we did up here, right, to the ketone. So this one, we want to do Markovnikov hydration with no rearrangement. So mercuric acetate, water, followed by sodium borohydride. That is the oxymercuration demercuration reaction. And then we want to do an oxidation. So again, PCC or sodium dichromate. Okay. How would you accomplish the first multi-step synthesis using a Williamson ether synthesis at the end? Okay, so if we're going to be using a Williamson ether synthesis at the end, right, and given that this part is in the reactant, we're probably going to be making this ethyl ether at the end, right? So that means that I'm going to simplify this to an alcohol, right? This primary alcohol. And then I can go ahead and add in the conditions to do the Williamson ether. Whenever you're using an alcohol, typically we use sodium hydride as the strong base. And then in this case, we would want to use ethyl bromide or iodide to introduce that ethyl group. So that's that Williamson ether synthesis. So then really it becomes a question of how do I get from this alkane, right, to this alcohol? Well, remember that when you're dealing with an alkane, there's only one reaction you can do. So that really narrows it down. You have to do radical halogenation. And it's best always to use bromide because that's the most selective of the halogens. And it doesn't matter where you want the bromine to go. The bromine will selectively go in the most substituted position. You can't choose, right? So that's where it's going to go no matter what. So now we have to deal with how am I going to get this into that? So I know that my functional group needs to change positions, right? Right now it's at this most substituted carbon and it's moving to a much less substituted carbon. So I can do a series of elimination addition reactions in order to move the functional group to another position. So the idea is we would want to first do an elimination of that bromine. Since it's a good leaving group, we can do that directly. In this case, we want to form the Hoffman alkene because that sets us up nicely to be able to do a hydration reaction from the alkene to produce the primary alcohol. And it looks like this is going anti-Markovnikov. So we want to make sure we know the conditions which will allow for that to happen. So first of all, let's do the E2 elimination to form the Hoffman product. So we want to use a bulky base to do that. And then from here, we want to do anti-Markovnikov hydration. So we want to remember that the conditions to do that are the hydroboration oxidation conditions. From an alkene, we write borane.THF, hydrogen peroxide, and sodium hydroxide. What is the difference between an isolated, conjugated, and cumulated diene? Which is the most stable, and how is that determined? Okay, so we have 3 different dienes, right? And I'm actually going to just go ahead and put those on an energy diagram, right? Because that's how we determine which is the most stable. Okay, so I want to think about the fact that the conjugated diene, right, is the most stable. So we want to draw that the lowest energy, right? So for example, we have a situation like this, right? This is a conjugated diene. And then maybe I'm going to make this a little bit bigger just so I can use the same number of carbons to form a isolated alkene. So that would be where they're alkenes, right? The p orbitals cannot overlap because they're not right next to each other. And then in the last case is a cumulated diene. I don't know if it's going to be more or less stable than the isolated diene, probably pretty similar. So 1, 2, 3 carbons, right? I'm going to do 4, 5, so I can have the same number of carbons. And I say probably pretty similar because these act as if they're isolated, right? Even though they're sharing a carbon, the p orbitals are going different directions, so there's no overlap to enhance the stability. So we'll put over here accumulated diene, right? And how do we tell which is the most stable? How is that determined? Right. Well, what we can do is hydrogenation, right? So we could hydrogenate, right? And we would add in 2 moles of H2 gas. So we're going to do, I'm going to write out hydrogenation reaction. Right. So 2 moles of hydrogen gas, which we would use in all cases. Oops. And we get the same product, right? So in this case, it would just be pentane. So that was why I was careful to always use 5 carbons. So this is a little tricky, right? Because sometimes people put a little dot here. So this means CH2C, CH, CH2, CH3. So there's 5 carbons there. Okay. So definitely the conjugated diene is the most stable. Right, which is determined by the amount of heat released during the hydrogenation reaction. Of the 3 isomeric dienes. Okay. Next question. How are conjugated dienes synthesized? Show the reactants and reagents that can be used to synthesize 1,3-butadiene. Okay, so typically they're synthesized through double elimination reactions. So for example, you might use this vicinal dihalide, and we could do double elimination, right, with excess potassium terbutoxide. So that should do, since this is bulky, it will come over here to these terminal carbons and do our E2 eliminations by removing a proton at the terminal carbons. If you were wanting to form an alkyne, through double elimination. Typically we use sodium amide, so NaNH2. NH2 minus is also a strong base, but it's much less bulky. So it can access these more hindered positions to do double elimination to form a triple bond here, right? So specifically, we are using the bulky base in order to get the diene. Okay. Show the major product at high temperature and at low temperature, which is the kinetic product and which is the thermodynamic product. Okay, so actually I'm going to take a little break here because I'm getting tired. And this looks like this is a long problem. So again, I will be right back. All right, going back to this, we have wanting to draw the products, major products at high and low temperature, and labeling them as kinetic and thermodynamic product. Okay, so what we want to do is think about where we're going to place the hydrogen first. And I'm going to form more than one product. So I'm just sort of drawing two carbon scaffolds here. And we're going to place the hydrogen at one of the terminal positions of the diene. And since this is not symmetrical, we're going to have to analyze putting the proton here or putting the proton there. So if we put the proton at the top, right, then the carbocation would be between these two positions. So it would be allylic, right, and it would be shared. And so we'll end up with the bromide either at the 2 position, right, or at the 4 position. So if the bromide ends up at the 2 position, 3 and 4 is a double bond, or the bromide could end up at the 4 position with the double bond shifted to between 2 and 3, right? We would call this a 1, 2 versus a 1, 4 adduct. Now, because there isn't symmetry here, if we were to place the double bond at the bottom terminal carbon, let's say here, right, then the bromine could go at the 2 position, leaving a double bond between 3 and 4, or it could switch here and we could put the bromine at the 4 position, right? So this would be 1, 2, 3, 4. So again, the 1, 2 adduct versus the 1, 4 adduct. Okay, so notice how either way, right, the proton either went to one of the 2 terminal positions of the conjugated diene, not one of the internal positions. The reason why it goes at the terminal position is that leaves us with an allylic carbocation, which is more stable than an isolated, non-resonance stabilized carbocation. So if we actually look at these structures, what we'll notice is that this is the only one that puts the bromine at the tertiary position. And if you take this and flip it over, right, these are actually the same structure. So we actually drew the same thing twice. So in this case, the 1, 2 and the 1, 4 adduct are actually, they work out to be the same structure. And they're different than these 2 products. So we could get, potential of up to 3 products here. The kinetic product is always the the 1,2 adduct, which again, in this case, and I think I didn't intend for it to be so complicated, this is technically both the 1,2 and the 1,4 adduct, right? And this is, separate. So you could argue that these two would be the kinetic product and these two would be the thermodynamic product. So you get more than one, which is sort of a complicated case, I think. So I almost think it might be worth it just to simplify this and, talk about it as if it was symmetrical. Like, let's say there was, no methyl group here or two methyl groups, so that there's symmetry here. Might be an easier case than this one is a little inadvertently complicated. Probably won't be on the exam. So I think what we'll do is I'll just put here accidentally a complicated example. So we'll just simplify it and look at, in fact, why don't we just look at this case? We'll put two methyls so that there is symmetry here. So we don't have to look at potentially 3 or 4 different products, right? So we're going to look at HBr, and then we're going to draw the products here. Remember, we're going to look at 1,2 and 1,4 addition, right? So I'm going to sort of draw 2 scaffolds and then use a different color just to show if we put the hydrogen at the top, and again, top and bottom is the same because of symmetry here, then it's possible that we would have the bromine here, right? Or here. So think 1,2, right? Versus 1,4 product. So this is definitely a much simpler case since there's only 2 different products, right? And we want to look at, okay, 1,2 adduct, right? This is always the kinetic adduct, okay? Because of the proximity effect. And the thermodynamic product is the more substituted alkene. So this is a tri-substituted alkene, right? Tri-substituted. And then this one is a tetra-substituted. And if you don't know how I'm getting that, what I'm doing is just counting up the carbons attached to the 2 sp2 hybridized carbons. So 1, 2, 3, right? How many carbons are attached to these two? 1, 2, 3, 4. So then the more substituted one is the thermodynamic product. It's not always the 1,4 adduct, right? But it is in this case. And it is whichever one is the more substituted alkene. So the kinetic product is formed as the major product at low temperature. And the thermodynamic product is formed as the major product at high temperature. And I think I'll go ahead and switch the example out on this for a more simplified case. And then the mechanism for this, we're going to draw out actually in the very last question on this mastery assignment. Okay. Explain how the Gibbs free energy equation. Sorry, it just got really bright outside, so I thought I'd close the shutters a bit. See if I can get it to focus. Shows why the Diels-Alder reaction is favored at low temperature. Okay, so let's go ahead and take a look at that, right? So we have, so the Diels-Alder, just like a simple case, right, would be a diene. And of course, it can have substituents, right? And a dienophile, which typically has at least one electron withdrawing group attached to it. And then those are reacting to form a cyclic structure. So a cyclohexene derivative, right? That's the Diels-Alder product. Okay, so if we think about the Gibbs free energy equation, we know that delta G is equal to delta H minus T delta S, right? So we know that delta H is the enthalpy term and delta S is the entropy term. So for this reaction, right, we have a net gain of 2 sigma bonds and a net loss of 2 pi bonds. Right? And because sigma bonds are stronger than pi bonds, you can think of it as like we're putting in the energy to break 2 weaker bonds and getting out the energy of forming 2 stronger bonds. So overall, right, the enthalpy term for the Diels-Alder reaction is negative because, again, we're supplying the energy to break 2 pi bonds, which are weaker bonds, and getting out, right, the energy of forming 2 stronger sigma bonds. So that is negative. So that's, one factor. And then we want to look also at entropy, which is delta S. So what we can see is that it's sort of like an A plus B equals C case, right? So we are combining 2 things, right, to form one, which is not favored in terms of entropy. And in addition to that, we're taking 2 structures that are not part of a ring and forming a ring, which limits conformational flexibility and rotation, which is also not favored through entropy. So one of the things that's hard to remember is that enthalpy when favored is negative. Entropy when favored is positive. So because this is not favored in terms of entropy, the delta S is also negative, right? So, and that's because we are forming, so here, right, kind of put the explanation. So we're forming a ring which has less conformational flexibility and taking 2 reactants to form one product, right? Which both of those are not favored in terms of entropy, and not favored means negative, right? Because favored would be positive. Okay, so really we have to think about the fact that we are taking the negative of a negative number, right? We're subtracting a negative number. So when we subtract a negative number, right, we're really adding the number. So these 2 together are actually positive, right? Because you're subtracting this number, which will overall be negative. So if we want this reaction to be favored with a negative delta G, then delta H has to be greater in magnitude than T delta S combined when multiplied together, right? And the temperature is multiplied, right, by delta S, or the entropy. So if we want this reaction to be favored, right, so for negative delta G, right, we want this to be think of it as higher magnitude or more negative, right? And this one over here should be lower magnitude. So basically you want to have this be a larger negative number than this is a positive number, so that overall it will be negative, right, when you add those together. So we want this to have overall a lower magnitude, which means we want a very small number for temperature, right? So we want T to be, quote, smaller, right? So that when you multiply it by delta S, overall it's a smaller magnitude, which means lower temperature, right? So therefore, right, the Diels-Alder reaction is favored at lower temperature. Okay. Draw the molecular orbitals formed from unhybridized p orbitals. Sometimes if I put a pen there, it will stabilize. In butadiene, which is the HOMO and the LUMO? What do these terms stand for? What is the term that is used to describe both of those orbitals? What does light do to electrons in molecular orbitals? Okay, so we have 4 neighboring p orbitals, right? So we can sort of draw 4 neighboring p orbitals, because remember that we're looking at butadiene structure, right? So there's a p orbital at every single carbon here, and those are depicted by these p orbitals, right? So 4 p orbitals, and they're unhybridized, right? So that's another thing to put in here for our notes. Okay, so when we use these to form molecular orbitals, because we took 4 p orbitals, we are going to form 4 molecular orbitals, because that's one thing that molecular orbital theory tells us, right? The number of atomic orbitals combined equals the number of molecular orbitals formed. So we're going to have a series of 4 different molecular orbitals. Right, and so we are going to call the bottom 2 bonding molecular orbitals, and in this case pi, because we're forming them from p orbitals. And then we have 2 that are anti-bonding. And sometimes those are called pi star as an abbreviation. So this is sort of an energy, right, scale here. Okay, so we have, these would represent our atomic orbitals forming the molecular orbitals. Anything that is lower in energy will be called bonding. Anything that's higher in energy than the original 4 atomic orbitals is anti-bonding. Okay, so we can go ahead and draw in these p orbitals. This is sort of a simplified drawing. And remember that as we go up in energy with molecular orbitals, we increase the number of nodes. So here we have 0 nodes, and then we would have 1 node, and then we would have 2 nodes, right? And then we have 3 nodes. And those are regions where there's zero probability of finding electron density. So we often just shift the phase. Okay, so you might see these as drawn something like this, with one side colored and the other side not colored. So I'm going to shift phase here whenever I reach a node. So you might ask, could I have started with down, down, up, up? Yes, that would have been fine. Oh, I messed that up. Sorry. Oh, I'm going to have to redraw that. It's going to look like this, though. Okay, I'll have to redraw that one. Okay. We're going to draw in the energy levels here. And since there's 4 electrons, right? These 2 are filled. So it wants to know what's the HOMO and what's the LUMO. So this one is the HOMO. And it stands for highest occupied molecular orbital. And then we would have also the LUMO, which stands for the lowest unoccupied molecular orbital. And when it says occupied or unoccupied, it's talking about electrons, right? So this is the highest energy orbital occupied with electrons. And this is the lowest energy orbital that's not occupied with electrons. And the term that's used to describe both the HOMO and LUMO together are the frontier molecular orbitals, because that's where the chemistry is happening. What does light do? Right? So light will promote an electron from the HOMO to the LUMO. Right? So light can promote an electron from the HOMO to the LUMO, creating a new HOMO and LUMO. Because if one of these electrons is up here, this is now the new HOMO, and this is the new LUMO. So that is, I think, all we need to answer the questions here. Explain why an aldehyde, ketone, cyano group, nitro group are all electron withdrawing from a pi bond. Hint, show resonance. And why is an alkoxy group overall electron donating? Okay, so we definitely want to show resonance, right, to explain this. So basically, if we look at a double bond and we draw an aldehyde, right, or we draw a ketone, or we draw a cyano group, which you could draw like this if you draw it out instead of writing CN, and then a nitro group, would look like that. So put in some electrons here since we're going to be drawing resonance. In that case, we always draw in all the non-bonding lone pairs. And so if we're drawing resonance, right, we can start with pi bond between atoms of differing electronegativity. And we always give those electrons to the more electronegative atom. Don't forget, if you're drawing resonance, to draw a resonance arrow, which is not the same thing as an equilibrium arrow. And then let's draw what we formed here. You can draw the C in here if you want, or just leave it kind of like as a dot. So most people actually, in this case, wouldn't really draw this particular contributor because it's not significant, but we can go ahead and draw it just so we can see the correlation in all of these cases, right? And then from here, we can do the allylic lone pair, or sorry, allylic carbocation pattern, right? So we're gonna shift these electrons over. So again, we started off with the pi bond between atoms of differing electronegativity pattern, followed by the allylic carbocation or the allylic positive charge pattern. And then if we draw what we formed here, okay, right? So what we see is that overall, we are actually removing electron density from the ring in terms of the pi system, right? Because you can see all of these green arrows are moving electrons out of the pi bond, right? So these are all considered electron withdrawing groups, right? So we'll say electron withdrawing groups because resonance shows electron density being pulled out of the alkene, right, which is the carbon-carbon bond in all of these cases. Okay, so how does that compare then to an alkoxy group? So if we had the same alkene, right, and we had an alkoxy group attached to it, the only pattern we can do in that case is the allylic lone pair, which actually pushes electron density into the pi bond. So we'll say that this is an electron donating group, right? Because resonance shows electron density being pushed into the alkene. Of course, it does pull electrons out inductively, but resonance is a much more dominant factor. And so overall, electrons are being donated into the alkene more than they're being pulled out inductively. What is the product of this Diels-Alder reaction? How is the endo rule used to explain the stereoselectivity? How is resonance used to explain the regioselectivity? Okay, so we want to draw the product. Since this is a cyclic structure, we're going to end up forming a bicyclic product. So we can, in order to do that, we can sort of start here. And then this is going to be a 2-carbon bridge. So I'm just going to kind of come up 1, 2, right, to form that bridge. And then forming the new sigma bonds down to these 2 carbons. So those two are the new sigma bonds, right, to the two carbons. And then here is the double bond that will form between these two carbons. We've got this dimethyl amino group we can draw in as well, right? That will be there. And we do need to consider regioselectivity, right? Because there's no plane of symmetry in the diene and there's no plane of symmetry in the dienophile. So we need to think about the fact that the nitrogen will push electron density to this carbon. So this one is delta negative, and that the nitro group will end up pulling electron density out right through resonance to give us the delta positive on the opposite carbon farther away from the nitro group. So we actually would want to, right, flip this over, and the nitro group will end up on this carbon, not that one. And we're gonna, because of the endo rule, we're gonna draw it pointed down. Okay, and there's no plane of symmetry here, so we're also going to form the enantiomer from the top approach of the dienophile. Okay, so how is the endo rule used? And what about resonance, right? So we kind of showed the resonance here. We can draw that out completely. Okay, and then we didn't really show it here because we need to draw out that nitro group, right, to start the drawing the resonance contributors, right? So here, and then what we'll do is we'll draw this out. And we just drew this on the last problem, but we'll go ahead and draw it again on this problem. And in this case, I'm just going to go ahead and do two arrows at once, just because I want to avoid having a resonance contributor with a 2 positive charge on the nitrogen. So I'll do the pi bond between atoms of differing electronegativity pattern, followed by the allylic carbocation pattern. You can just draw those at the same time. And that just makes it avoid forming anything insignificant. Okay, so resonance, right, shows us the delta negative and delta positive, which allows us to draw these in such a way that they'll form an electrostatic attraction, right? So we want to, if we redraw this, we can just flip over the dienophile. That's one simple way to do it. So I sort of flipped it over and then flipped it over again just to show it endo. But the point in this case was just to have the delta minus and the delta plus aligned. Right, so this is, right, our resonance shows the carbons with delta minus and delta plus, which form an electrostatic attraction. Basically, opposite charges are attracted to one another, right? So we have, right, those two being shown aligned here. Okay, and then what about the endo rule, right? Well, the endo rule we can draw, and again, it's a little bit challenging. We can kind of, because it's a cyclic structure, right? But we can sort of do our best here to attempt to draw this in such a way where we can see the difference. So we have these two, and then right below it, I'm going to draw the dienophile. Okay, so that's one orientation that they could potentially exhibit when the dienophile approaches from the bottom of the diene. And then as well, another possible orientation is with the electron withdrawing group, that nitro group pointed away from the diene. Okay, so what we're going to see here is some orbitals. Right, and there's even some here. And we're not really being asked to draw the formation of the new sigma bonds, right? Although we could include that if we wanted to. More looking at the secondary orbital overlap. So what we can say here, right, is we'll have primary orbital overlap, right? And then here we would have what's called secondary orbital overlap, right, with the endo approach. Whereas these would be too far away, right? So this is the exo approach, right? And there's no secondary orbital overlap. So as a result, the nitro group forms an attraction here that is temporary, but lowers the transition state energy, making this product form faster. And that leads to the nitro group being pointed down. So this stereochemistry here. So let's see if we answered the question. What is the product? We drew the product. How is the endo rule used to explain the stereoselectivity? Right, so this endo, which allows for secondary orbital overlap, right, predicts the stereochemistry, right, at that particular carbon. So endo leads, I'll call it approach, leads to nitro pointed down, right, which is the stereoselectivity. All right, next question. What is the product of this Diels-Alder reaction? Do we need to do an S-trans to S-cis rotation? How is the endo rule used to explain the stereoselectivity? Do we need to consider regioselectivity? Okay, so right now, this is drawn in an S-trans configuration. So yes, we do need to do a S-trans to S-cis rotation. So one way to think about that is just to sort of rotate around this central carbon-carbon bond, or think of taking this top piece and flipping it over like a pancake while leaving the bottom, right, exactly where it is. So what we can think about that looking like, right, is essentially flipping that over. So we would have the alkene like this, right? We would have the nitrogen with the two methyls. And then this would be pointed in. And one way to double check that we did that correctly is to think about E and Z, right? Or think of like this nitrogen is opposite this methyl, right? And so it should still be opposite the methyl. The stereochemistry about this alkene has not changed. We've just, rotated a bond, essentially. Okay, so what's E should remain E, and those two alkenes are E. Okay. So now that we have done that, right, we want to ask ourselves, do we need to consider regioselectivity? And the answer is no, because, right, there's a plane of symmetry here. So that means we do not need to consider regioselectivity. Because if you flip it over and it approaches, it's going to form the same thing. Okay, but these two electron withdrawing groups will favor the endo position. Again, due to favorable secondary orbital overlap, like we talked about in the last question. So we want to imagine that actually approaching with the nitro groups pointed in. And then we can think about forming the product, right, of the reaction. So with some gentle heating, right, low temperature ideally, sometimes gentle heating is okay. We will form the product. So we're going to have a cyclohexene derivative. This will remain trigonal planar, so we'll just draw it in the plane. This methyl is pointed in, so it will end up. And then these nitros are approaching endo, so they will end up down. There is no plane of symmetry here, so we would also form the enantiomer. Okay. Provide an example of a Diels-Alder reaction using an alkyne as the dienophile. How is the product different than if an alkene was used as the dienophile? Okay, so we can use an alkene, right? And then we can use an alkyne. So maybe we want to put an electron withdrawing group on there, right? So maybe we'll use an aldehyde. And the product would be, instead of a cyclohexene derivative, it is so we would start counting here. So 1, 2, 3, 4, right? A 1,4 cyclohexadiene derivative instead of a cyclohexene derivative. Okay, so we'll just label this. This is the dienophile. Okay, moving on. Show the mechanism of an LAH reduction of a ketone. Would sodium borohydride, or could it do the same reaction? Is an acidic workup necessary, and why? Okay, so let's go ahead and draw a ketone. And it sounds like any old ketone will do. So we'll just draw a simple ketone. And then we want to draw out lithium aluminum hydride, right? So you should know what that looks like. So that is an aluminum bonded to 4 hydrogens. The aluminum has a negative charge, and there's a lithium counter ion, right? So that's LAH. And it will, one of these hydrides can do a nucleophilic attack on the partially positively charged carbonyl carbon. A resonance arrow will move electrons up to the oxygen. And then we have this alkoxide, which does require a proton transfer from an acidic workup to become neutral and stable, right? So we do need an acidic workup. So dilute acid, very common here. And we're going to show proton transfer. Remember, with proton transfer, we start from the base, point to the proton, leave the electrons behind, and we need to show 2 arrows for every proton transfer, right? So this is a proton transfer. And the first step was a nucleophilic attack. And then the product. So we'll draw OH. We'll draw in this hydrogen as well, right? Kind of using color coding to show where they come from. And to answer the question, would sodium borohydride do the same reaction to a ketone? Yes, right? Sodium borohydride can reduce ketones and they can reduce aldehydes, but not esters and carboxylic acids. So we could say yes, sodium borohydride reduces aldehydes and ketones. And in this case, we're using a ketone. Okay, and then we'll put for, is an acidic workup necessary? Yes, to form the neutral alcohol product. Okay. So really, really important. You have to be able to draw out these mechanisms. I did this color coded. You wouldn't have to on an exam, just to try to show you what's happening in a way that's easier to remember, because colors help us remember things. Second question, what sort of substrates are best for an SN2 reaction? Primary, secondary, or tertiary? What about an SN1 reaction? Show an example mechanism for each with an alcohol reactant. Okay, so for an SN2 reaction, right, the best substrate between these choices is primary. And for SN1, right, the best would be tertiary. So let's draw a primary alcohol and a tertiary alcohol. And we're wanting to show an SN2 and an SN1 reaction. So a simple case might be the reaction of both of these with HBr. which will really illustrate the difference. So we're going to start off doing the same process, right, in both cases. So we're starting off with a proton transfer. Now this has effectively converted our bad leaving group into a good leaving group in both cases. And we've also formed some bromide. Okay, so here is where the difference in the two mechanisms occur. In this case, the bromide is going to do backside attack simultaneous with loss of a leaving group, right? So this is the SN2 step where we're doing a nucleophilic attack and loss of a leaving group in the same step to form the product. And we form some water. But that is not going to be the case with a tertiary substrate. That will undergo SN1 instead of SN2, which with SN1, we have separate steps. So first, we do loss of a leaving group. And next, we would do the nucleophilic attack. So those occur separately. To form the product. Show the mechanism for a Williamson ether synthesis. How does the choice of base change if the reactant is phenol versus an alcohol? So we have, let's look at an alcohol versus phenol. So if you recall pKa values, we know that the pKa of a phenol is about 10, and the pKa of most alcohols is about 17, right? Specifically looking at this proton attached to the oxygen, right? So this is, 10 to the 7 times more acidic, right, than this. So we can use a much weaker base to deprotonate this than if we needed to deprotonate a aliphatic alcohol or, something that doesn't exhibit resonance stabilization. Okay, so the choice of base, right? So in this case, we're going to choose, right, sodium hydride as base. It's a much stronger base than sodium hydroxide. So we require, right, a stronger base for the weaker acid. Okay, so we're going to do proton transfer to show the Williamson ether mechanism. So regardless of what base, we still show proton transfer. Remember the base, draw the arrow to the proton, leave the electrons behind on the acid to form the conjugate base. So this is going to form the alkoxide intermediate, and then the phenoxide intermediate in this case. And then the second step is the substitution with an unhindered alkyl halide. So it's going to undergo an SN2 substitution reaction. So we are going to draw in some sort of unhindered alkyl halide. Could be even just methyl would be the best case scenario because it's the absolutely least hindered type of carbon. Right, so we're going to show our SN2 process here to form the product. Okay. Show any example mechanism starting from an alkyl or aryl halide and doing a Grignard reaction. How do you know when to use an aldehyde ketone or epoxide as electrophile? Well, we really talked about how do you know which one to use in a previous question, right? Let me see what question that was. And I'll just reference that one. That was number 8. Okay, so for the answer to this question, right, we'll say C question number 8. So we already went through that process. Okay, so an example mechanism starting from an alkyl or aryl halide. Okay, so an alkyl halide would just be like any alkyl group, could be primary, secondary, or tertiary. And an aryl group would like be an aromatic ring directly attached to the halogen, right? So that would be an alkyl. And again, it can be anything, primary, secondary, tertiary. Here's the aryl case, right? And the first step is treatment with magnesium metal, right? So we treat this with magnesium metal, and then magnesium inserts between the carbon halogen bond, probably in a radical-like process. So what we can do to generate that is we can essentially show the magnesium, right, inserting between the carbon halogen. And we can draw the same thing here with the aromatic ring. And again, I'm using colors just to highlight how we just show the magnesium inserting between that carbon halogen bond. And then now it can react, right, with an aldehyde, ketone, ester, or even epoxide as an electrophile. So let's just do an example, and these would react the same way, right? So I'm just going to kind of continue on with this one because there's space, right? But they would react similarly. So now we would add in either the aldehyde, the ketone, the epoxide, something like that, right? So let's maybe add an aldehyde. And then we're going to show, and this is really important. So these electrons, right, are spending most of their time around this carbon. And this is the nucleophile, right? And this carbon over here, right, is the electrophile or the electrophilic center. So the nucleophilic electrons attack, right, the electrophilic center, and then a resonance arrow, right? This shows the formation of the new carbon-carbon bond. So that is a nucleophilic attack. Now we have this carbon directly bonded, right, to the electrophilic carbon. So we sent electrons up to the oxygen. So now we have a negatively charged oxygen. And there was a 3-carbon chain attached there as well. Right, so now we have formed our new carbon-carbon bond. And then we just need to show the acidic workup. Right, so at the very end, you would add water or dilute acid. Right, this is the quote second step, right, which is the acidic workup. And we want to show some arrows here to show proton transfer. If I want, I can stop drawing in this hydrogen just because we don't draw it in line structures, right? And then that hydrogen came from the acid workup, right? So in the end, we have the final product, right? So this step, we don't really draw any arrows, right? We just say magnesium inserts between the carbon-bromine bond. And then we show the nucleophilic attack, right? Followed by the proton transfer. Okay, remember, you are going to be drawing these mechanisms on the exam. So it's really important that you can do this. Practice by just drawing it over and over on blank piece of paper or on a whiteboard to make sure that you are drawing in all your arrows properly. Okay, so again, I'm just going to remove this methyl group, right, to make it a simpler case. And it says, draw the mechanism explaining how the 1,2 and 1,4 products are formed in this reaction and show resonance of the intermediate. Okay, so I'm going to redraw the diene. And I'm going to draw out HBr where I'm going to see the bond between the hydrogen and bromine. And that's important because as I draw this proton transfer, I need to be able to draw the arrow starting from that bond. So it is super important, right, that I draw that bond in. So this is a proton transfer step. And then that gives me, remember that we are going to always put the proton on one of the terminal carbons so that that leaves us with an allylic and resonance stabilized carbocation intermediate. All right, so this is a allylic carbocation. And there are two resonance structures. So we want to show both of those. We also form some bromide in the first step. And that bromide can either attack carbon number 2, right? Hence 1, 2. Or it could attack carbon number 4, generating two different products. Because remember, both carbon 2 and carbon 4 share the positive charge. So they're both electrophilic. So they both can be attacked by the nucleophile. So if we have attack at carbon number 2, right, we put the bromine at the 1, 2 position. Now, sometimes the hydrogen won't be drawn in, right? Sometimes we don't draw that in. So you want to imagine, though, that it went in. And you can add it if you want to make it easier for you. If the bromine ends up on the 4 position, it will end up there, right? So this technically is the 1, 2 adduct, but you might be noticing something already that I haven't mentioned yet. So you should ask yourself, are these actually different? Right? If I was naming those, how would I name them? So I would name it as an alkene, right? And I would want the lowest number for the alkene, and then moving on to the halogen, right? So I'd go 1, 2, 3. So 3-bromocyclohexene, 3-bromocyclohexene. So those are actually the same structure, right? So you can say like, oh, a mechanism how each is formed, but really they lead to the same product in the end, in that case. Okay, give an example of, let's wait for that to focus. A Diels-Alder reaction where regioselectivity must be considered. Draw the resonance contributors of the diene and the dienophile to show where the partial positive and partial negative charges exist. To explain the correct alignment of the diene and dienophile, show the curved arrow mechanism of the Diels-Alder reaction. So it says I can give any example that I want, right? So I am going to show this case. Let's do a nitrogen. Right, so I'm going to use this diene. And then I'm going to use maybe a different color for the dienophile. I am going to use an aldehyde ketone. Maybe I'll use a ketone. Doesn't matter. Okay, so this is the dienophile. So it says it wants us to show resonance, right? So let's go ahead and do that. So we have an allylic lone pair. So we can draw the allylic lone pair pattern. And then we can actually keep going with the allylic lone pair pattern. Not in focus very well. See if I can help with that. Okay. So now we are going to draw in the last resonance contributor. Okay. And then for the dienophile, we can draw resonance. We'll start with pi bond between atoms of differing electronegativity. Followed by the allylic positive charge, also known as allylic carbocation. Okay, so specifically, we are interested in the terminal carbons of the diene, right? The fact that the negative charge ends up here doesn't really matter, right? So between these two, this carbon has the negative charge and this one never does, right? So if we're kind of, in the end, coming back to the original structure, right, it matters which either this one, right, or this one has the partial negative charge, right? And it's this one that has the partial negative charge. And then with the dienophile, we come back to the original structure, right? We have the positive charge, right, either ended up here or here. So we care about it if it's one of the carbons that's going to form the new sigma bond. And this one ends up with the partial positive charge, right? So this then shows us that this is the correct alignment, right? So the opposite charges are aligned to maximize electrostatic attraction. And we'll say leading to the major regioisomer. Right, so we can then figure out what the product is going to look like, right, with the right regioselectivity. So is the aldehyde going to be here or, you know, flipped over and down here with respect to the positioning compared to the dimethylamino group, right? So that dimethylamino group, it will stay here and the aldehyde will be right next to it, right? So this leads to the major regioisomer. Okay, let's see if we answered all the questions. So we didn't answer why this is a case where regioselectivity must be considered. So we'll say neither the diene or the dienophile have an internal plane of symmetry. So in this case, regioselectivity must be considered. We drew the resonance contributors. We showed the positioning of the partial positive and negative charges, which explained the correct alignment of the diene and dienophile, right? We did that here, oops, down at the bottom. And then it says, show the curved error mechanism of the Diels-Alder reaction. So that's something we did not do yet. And I'll just draw this again, just so, because I already have a lot going on this structure. So just to simplify, so there's our diene. Here's our dienophile. We actually know that the aldehyde will point in because of the endo rule, but this is still the correct alignment, right? And we want to show the mechanism, right? We're going to be forming bonds between those two sets of carbons. So we can just do a clockwise or counterclockwise, right, shift of all the pi electrons. Okay, so this is the mechanism. It's one step. So we call it a concerted reaction because it's everything, all the electron shifting is happening in one step. And we need these three arrows drawn, right, in a circular fashion. And then that shows us, right, we get the product from there. So it didn't ask us to draw it, but we'll go ahead and draw it in this case. So because this is pointed out, right, this will end up down. And then this is going to be endo, so this will end up down. There's no plane of symmetry here, so we have to write plus enantiomer. Sort of carve this out from the rest of it. Okay, so that concludes the mastery assignment. Hopefully, if you go through that, you'll feel really confident in your knowledge and ready for midterm 1.